In this lecture, we're going to talk about the eigenvalue problem, or specifically numerical solutions to the eigenvalue problem. And this will be the first of probably two videos. In this first video, we're just going to talk about how to solve for the largest eigenvalue, and then we'll talk about techniques for solving all eigenvalues in a future lecture. So just to recall, for context, as engineers, we encounter the eigenvalue problem in computing principal stresses of the stress tensor, in solving for vibration modes in dynamics problems, lots of applications in computer vision and other things in machine learning. But mathematically, the eigenvalue problem is this problem. Given a matrix A, find the values lambda, the scalar values lambda, that correspond to this solution, okay? And in order to do that, we rearrange the equation so we're just moving everything to the left, leaving a zero vector on the right-hand side there. And then for this solution to be non-trivial, that is, we're not interested in the solution where x is equal to the zero vector, the vector x is equal to the zero vector. For the non-trivial solutions, then this must be true. And when we solve for that, it gives us something called, when we solve the determinant of a minus lambda a, it gives us something called a characteristic equation, in which the roots of that equation give the values of lambda. So let's look at how we might be able to solve for this numerically. We're going to start just by, this method is called the power method. And we're going to start by defining a vector x that's equal to some scalar factors bj, beta j, times the j eigenvectors, right? So this is just, the summation implies, that this is a linear combination, right? So for a 3 by 3 matrix, there would be 3 eigenvectors, Vj, and then in this case, we're going to have these undetermined scalar values, Bj. So if we take this equation here and we multiply on each side of the equation by a matrix A, so if we get a matrix A, then what you'll notice is what is here we have, if V is an eigenvector, then we know that A times V is equal to lambda times V. So we can replace that or establish this equivalence as well. And if we then multiply this equation by A again on the left-hand side, then we get this, and we continue this sequence such that if we multiply K times, A K times, then we ultimately have this equation down here. Now, for this equation here, I'm just going to do something kind of special. I'm going to multiply both sides of the equation by 1. Okay, so 1 on the left looks like that, but on the right hand side, I'm going to multiply. My 1 is going to be lambda 1 to the k over lambda 1 to the k, right? So I think you'll agree that that's just 1. But then what that's going to allow me to do is group these guys together, and then I'll have the lambda 1 that I can put out front there. And so that's going to give me finally this equation here. So once I have that equation, there's something we can notice about it, and that is, I guess I didn't clearly define what lambda 1 is, but lambda 1 is the largest eigenvalue. So the magnitude of lambda 1 is going to be larger than all the other eigenvalues, okay? And if that is the case, for j greater than or equal to 2, right? So if we look at this summation, for any, for j equal to 1, well, this is just 1 over 1. 1 to any power is going to be 1. But for j equal to 2 or greater, then we're going to have some number that's smaller than lambda 1 divided by lambda 1. And so as we take k to infinity, this, as we take k to a large number, this is going to converge to 0. And then all we'll be left with is this final relationship. And we can show that or prove that this is always convergent as long as lambda 1 to the lambda 1 is less than 1, sorry. So this is convergent as long as lambda 1 is less than 1. And we can ensure this convergent by taking a sequence of vectors x and scaling them in a proper way, in an algorithmic way. And so let's take a look at how we might do that. So we'll start with, we'll take our vector x, and we'll define the first in a sequence of a bunch of vectors x. What we're going to do, so in this case I'm using the superscript to be our iteration number, like the number in the sequence of vectors we're going to take. And what we're going to do is we're going to define a component of the x vector to be equal to the L infinity norm. So basically this is just mathematically saying, look, we're going to find the largest value in the vector x, and we're going to scale it to 1. Okay? And so if we do that and plug back into our relationships earlier, defining a couple other things, namely that now we have a vector y that is equal to a times the vector x, the initial value, and then this value mu, which is going to be equal to the component of y, again, that is given by this type of definition up here, that the component of y, the largest value of y when scaled to 1, okay? And so if we plug that back into our equations and just do some manipulation, ultimately we can factor out the lambda 1 here. And so that's what we have for, given the definitions of our initial vector x and a second iteration 1. And if we continue this sequence, basically swapping, allowing 1 equal to 2 and 0 equal to 1, continue to develop a sequence like this. Again, with these definitions, ultimately what we'll end up with is this equation down here. And what we have for this equation is for large m, this term goes to 0, this term goes to 0, and then you're just basically left with this term which goes to 1. And so therefore, as m goes to infinity, then mu approaches the largest eigenvalue, lambda 1. And so the pseudocode for the power method basically is just what we've done there. We initialize an eigenvector. It can be anything. It just the only thing it can't be is something such that a times that vector is equal to 0. So mathematically, we'd say that it's in the it can't be in the null space of the matrix A. So as long as it's not in the null space of the matrix A, it can be anything. And from there, we'll just set an initial error greater than some tolerance. Find the smallest integer p. Basically, this is the index location in x of the largest value. And then we'll redefine x to be the vector x divided by that largest value. So what we're doing is we're normalizing it such that the largest value in x will be 1. And then we run it through our iteration. So y is a times x. Mu is the largest component of the p component of y, and then we find a new p associated with this, set our error bar to this, set a new vector of x. We proceed through this loop until error reduces below some tolerance, and then we break out of that loop, at which time our value of mu would be the largest eigenvalue, and the value of x would be the associated eigenvector with that, where the largest value in x is 1. The rate of convergence for the power method is equal to this guy. We're going to skip the details of that. So here's a simulation for this matrix in 2D with an initial vector guess of 1, 0. So that's represented by this dashed line here. our initial value of the eigenvalue will just initially be 0. The true value here is 1.1. So what we'll see when we play this is that the iteration proceeds through, and it does in fact converge. The eigenvalue is the red dot going through the loop. Each time it gets closer and closer to the exact value, as does the eigenvector converge to the eigenvector. So we can improve the convergence rate of the power method by just modifying it. This is called the inverse power method. So basically what we're going to do is we're going to apply the power method to the problem, or to the matrix rather, A minus Qi inverse. So we're going to basically apply the power method. So if we had a function that was defined on a matrix A, we would just essentially call that function on this matrix, where Q is a value that's close to the eigenvalue of the solution and eigenvalue of the problem. And so with that, then I'm going to skip all the details, but with that we can get a convergence rate of this, where again Q is some value that's closest to the kth eigenvalue. And so you can improve, the closer Q is to lambda k, then the faster this will converge. So then here's the pseudocode, and again, it's essentially the same thing. We do have to have an initial guess for Q, which we use this projection here as a good estimate. Other than that, it's essentially identical to the power method, just with everywhere you saw A before is replaced with A minus Qi, and in this case, it's A minus Qi inverse, which in this case requires a linear solve at this step, right? And you can do that with any method that we've discussed up to this point. So once we have the eigenvalues, then we can use this so-called deflation technique if we wanted to solve for others. So for example, what we could do is we can choose an integer p to be an index, to be any index that's non-zero, or any index where the component associated with the eigenvector we found, in this case we'll assume it's the largest eigenvector, the lambda 1, such that we choose p to be a component of x, so we'll call that x1p, and as long as this is non-zero, this will work. And what we're going to do then is we'll establish a matrix B that's equal to A where the double overbars indicate a matrix, and the single indicates a vector. So in this case, A vector P is the pth row of A in the definition here. And so what this does is it deflates the matrix A to establish a new matrix B, which B will have the same eigenvalues as A, except the largest eigenvalue will have been replaced with a 0. And so then what we can do is run power method or inverse power method on B to solve for the next highest eigenvalue, deflate that matrix one more step, so you run it again, and we can continue to do this to solve for all the eigenvalues. Turns out that these deflation techniques are not that stable or numerically robust, and there are other methods that we can use to solve for eigenvalues and eigenvectors, and those will be the subject of a future lecture.